Hello. In this video, we're going to take a look at the tutorial for AP Physics 1 homework dynamics. Let's start with section 1, horizontal forces. Question 1. An object of mass 100 kilograms is at rest on a horizontal surface where the coefficient of static friction is 0.8 and the coefficient of kinetic friction is 0.6. A person's hand applies a force to the object directed to the right. Draw the forces acting on the object. Well, we should see a weight balanced with the object, normal force. I'm balancing those two forces there. Okay, friction. Friction is fun, going to the left. Why is it going to the left? Because we know the object is directed to the right. And a force applied to the right that's greater than that force. Why do we know that the applied force F is greater than friction? Because the object is accelerating to the right. So this force must be greater than that force. Okay, so to complete your points on this, we need to know that normal force needs to be balanced with weight. Normal force up, weight is down. That friction is right, or friction is left, applied force is right. And that friction is less than both the normal force and the applied force. Part B. The block is not initially sliding. Calculate the minimum amount of friction needed in order to do this. So in order to get the block into motion, the minimum amount of force, F, balances your static friction, which is equal to mu times normal force. But that's going to be equal to mu times mg, since normal force balances the weight. So this minimum amount of force is going to be the coefficient of static friction. So we're going to use 0.8 times 100 times, go ahead and use 10 for G. For all problems in this right here, use 10 for G unless the problem tells you otherwise. Okay, 100 times 10, of course, is 1,000, times 0.8 is 800. So we must overcome 800 newtons of force in order to get the object into motion. Part C, assume that the blocks have the same amount of force applied after the block is set into motion. Calculate the acceleration of the block while it slides. So this is where we're going to use Newton's second law. Causing force, Newton's second law tells us that a net force equals ma. The net force part of it is causing force minus opposing force equals ma. Well, the applied force is our causing force. That's our causing force right there. And the friction, that's our opposing force. But here's the difference. We're now sliding, so we now have sliding friction, kinetic friction, not static friction. So we have to account for that. So minus kinetic friction equals ma. That's going to be the same as F minus mu k, that's 0.6, times normal force equals ma. But that's going to be mu k times mg equals ma. Divide out the mass, solve for a. And the same amount of force as applied in the previous example, part B, is 800 minus mu sub k is 0.6 times mg, which would be 100 times 10, all divided by the mass. The mass was 100. And so basically we get 800 minus 600 is 200, divided by 100 is 2 meters per second squared. A block weighs 100 newtons and is placed on a horizontal surface where the coefficient of static friction is 0.6 and the coefficient of kinetic friction is 0.4. Suppose that the horizontal force is applied to the block directly to the right. Probably be a good idea to draw a picture of what's going on here. Here's the block. We're applying a horizontal force to it. You've got the weight of the block, which is 100 newtons. Since the force is horizontal, that means the normal force completely balances the weight and is also 100 newtons. Now, if we're talking about there being coefficients of static and kinetic friction, that means friction acts to the left. And friction is equal to mu times normal force. So we're going to keep this information in our hip pocket to help us figure out what to do in this problem. So in part A, for this part, assume the block is initially at rest. So what this means is it's at rest because static friction is preventing the motion. Okay, what is the block doing in this case? It's not moving. Because static friction is preventing the motion. Now, one thing we should do is figure out what static friction. So static friction is Fs. Kinetic friction is Fk. Should figure out these values to be able to apply to them. There's a force of 50 newtons. And the static friction force would be 0.6 times 100, which is the normal force. So the static friction force is 60 newtons, and the kinetic friction force is going to be 0.4 times 100, which is 40 newtons. Okay, so why is the block not moving? Well, the applied force is 50, and static friction well, actually, that's for the next part, so let me go ahead and erase that. Part 2, what is the force of friction acting on this block? It's static friction. Right, because the block is not moving. And one thing to state about why it's not moving, back in the first part, is that the applied force of 50 newtons is not enough for the maximum static friction of 60 newtons. So in other words, the lowest amount of force that you can apply to get this thing moving is 60 newtons, which happens to be the maximum static friction that's holding this block in place. Now in part B, assuming that the block is initially sliding to the right, now we're talking about kinetic friction. What is the block doing in this place? Well, the block the block is moving, but really the block is accelerating. Let's think about why. Because the forward force is always 50 newtons, but this time the backward kinetic friction is only 40 newtons. The forces are not balanced. Therefore, there's a net force of 10 newtons pointing to the right, causing an acceleration to the right. The applied force of 50 newtons to the right exceeds the 40 Newton kinetic friction force to the left. Okay, what is the friction force? Well, it's kinetic friction. Because block is sliding. Over the surface. Number 3. When moving heavy furniture, people often lift the furniture completely off the floor in order to move the furniture to a different point in the room. Suppose that two people attempt to move a heavy couch. When they attempt to lift the couch, they cannot together exert enough upward force to balance the weight of the couch. So they decide to slide it across the room, across the carpet floor, in order to set the couch into its new position. Is it helpful for two people to exert a lifting force on the couch while moving it, even if they cannot lift the couch off the floor? Explain why. Well, lifting the couch reduces the friction force. Okay, here's why. If you took a look at a picture, say here's the couch, okay, on the floor. If two people are exerting an upward force on the couch right here to be able to lift it, you got the weight of the couch exerted on the floor. You've got the normal force exerted up from the floor, and friction is equal to mu times normal force. So if you provide an upward force while you scoot it across the floor, you're going to lessen the normal force, which means you'll lessen the amount of friction. So yes, this is a helpful approach. Lifting the couch reduces the friction because, let me just kind of finish off this sentence, because it reduces the normal force. Number 4. An ideal block is set on a rough table and connected to a hanging mast by a string that passes over an ideal pulley. The system is released from rest at time equals 0 and speeds up as the mast falls. Once the mast strikes the floor, the block comes to rest again. The student uses measurement apparatus to collect data of the block's velocity as a function of time. The data are shown in the graph to the right. So, before we even begin the problem, the first thing I'm thinking as we see this is I'm seeing two masses connected by a string. Therefore, I'm thinking multiple mass tension, okay, multiple mass acceleration. That's really, this is a Newton's second law, multiple mass acceleration type of problem. And what do we do with the Newton's second law multiple mass acceleration problem? Well, one, we figure out the forces acting on the system. We figure out the forces acting on each mass, of course, but you're going to figure out the forces acting on the system of masses because you're going to exclude internal forces like tension, and you're only going to focus on external forces like friction, like weight, like applied force, things of that nature. So that's the first thing I see is this picture here is showing me multiple mass acceleration because we have two masses that are indeed accelerating together. Then I look at this picture and I see a velocity time graph. And one of the things I should remember is that there are two things we know from a velocity time graph. One, the slope of the velocity time graph equals acceleration. Okay, so I need acceleration for multiple mass, so I can get acceleration from this graph. Two, the area underneath a velocity time graph is the displacement. Now that's fine if it is a kinematics-based question where it's asking you how far the block slid before it came to rest. That's fine. Then you need the displacement, and you can get that information from different parts of the graph. So we're going to be using this portion right here. So what I'm going to do is I'm going to find the slopes. You can see that there are two slopes here, one here and one here with the data. The first slope looks to be up 8 over 4. That would be a slope of positive 2 meters per second squared. And then that would be from 0 to 4 seconds. And then from 4 to 6 seconds, we look to have a downward slope going down 8 over 2, which would be negative 4 meters per second squared. Now, what's supposedly happening here? From 0 to 4 seconds, let's map this out so we understand what's going on. From 0 to 4 seconds, the 5 kilogram block, which is the horizontal one, speeds up going forward. That's what this line is telling me. That positive constant acceleration there, that is speeding up going forward. And that makes sense. The block is starting from rest. The tension in the rope yanks it to the right, and it's speeding up as it's going forward. But once the second block hits the floor, this block is now further along, and friction is going to slow it to a stop before it reaches the end of the table. So now I know from 4 to 6 seconds, the 5 kilogram block is slowing down going forward. So in both cases, that 5 kilogram block is going forward, but this is a case of slowing down going forward. This is a case of speeding up going forward. So it's very, very helpful to take a second to interpret the motion of a position, velocity, or acceleration time graph, because you need that information in various parts of various questions. Okay, now let's see how we can use this. Part A. For each time instant as shown, draw a free body diagram showing the forces on the 5 kilogram block. Okay, so the 5 kilogram block is going to have two vertical forces, weight and normal force. And you can kind of sketch it up here. We're going to have weight going down, weight equals mg going down. You're going to have normal force going up. You're going to have tension going to the right, and you're going to have friction going to the left. Here's what you need to do in your free body diagram to get the points. One, you need to have these two equal to each other. They have to balance. Two, you have to make sure that your leftward friction is less or shorter than normal force. And that's because friction is equal to mu times normal force, and mu is a decimal that is less than 1. So friction is always less than normal force. 3, since the block is accelerating to the right during the first 4 seconds, tension must be greater than friction, so draw tension longer than we draw friction. So those are the things that we are thinking about for the first 4 seconds while it's speeding up. During the second segment where it's slowing down, well, when it's slowing down, you no longer have tension because now the block is over here. It's now the motion would be to the right still, but now the acceleration is to the left because you're slowing down going forward. And the only force that's causing that acceleration to happen is still the same friction that you have before. Same friction. You just do not have tension anymore. Okay, so that's where we're going to go with this. Now, we can see at t equals 2 seconds, t equals 2 seconds would be in the first time interval right here. You can see where 2 seconds falls. And so I'm going to draw a free body diagram that has, I don't know, I'm going to go, I guess, 5 units down. So weight equals mg. I'm going to balance it with normal force. I'm going to make sure friction is shorter than normal force, and I'm going to draw tension just a little bit longer on the right-hand side. Okay, what is my net force? Remember, net force is causing force minus opposing force equals ma. Well, your causing force is going to be your tension because you're accelerating this way. So the causing force is tension minus the opposing force, which is the friction. So tension minus friction equals ma would be our first free body diagram and our first equation, our Newton's law equation. During the second time, so 5 seconds occurs during the time interval where we are decelerating or slowing down. And so during that time, you have the same amount of friction. So I've got that 3 Newton thing going to the left, but I've got nothing else going horizontally. I still have the same normal force and the same weight acting on the block. So now if we're looking at causing force minus opposing force equals ma, my causing force would be friction minus nothing. There's no opposing force. Because remember, the block is sliding this way, but since you're slowing down going forward, acceleration always goes opposite motion when we slow down. It goes with motion when we speed up, but it goes against motion when we slow down. So those are our 2 equations for, our 2 Newton's law equations for part 1 when we speed up going forward and part 2 when we slow down going forward. Part B, calculate the following using the equations above. So for parts B1, to get kinetic friction, well, let's use the second equation where all we have is friction. That makes sense. So we can go friction equals ma, and the kinetic friction force is going to be the mass of the block, which is 5 kilograms, times, okay, and keep in mind, we're finding the magnitude of it. Okay, friction is negative because it's causing a negative acceleration, okay? But I don't need to know that because it's just, we're trying to find the magnitude, the amount of the kinetic friction. So it's 5 kilograms times, go back and look at the chart. Remember, we found the acceleration to be -4. Again, the negative just tells you about the direction or the qualitative nature of the acceleration, okay? The fact that we're decelerating going forward, basically. So I just need the 4. And the friction force would be 20 newtons. Kinetic friction of 20 newtons. Now, for part B2, to find the tension force, that's where we're using the other equation. So the other one is T minus friction equals MA. And to find tension, I'm simply going to add friction to both sides. So tension is equal to friction plus MA. Tension is equal to 20 newtons plus 5 times. Now, we want to know, if you want to know the tension, now you want the acceleration during the first interval, which is the 2 meters per second squared. So 20 plus the 10 would give us a tension of 30 newtons. Number 5. A car of mass m is fitted with tires that have a coefficient of kinetic friction with the roadway of mu. The car initially moves with speed v to the right. Now, since they're calling it speed v, that initial speed usually was called v naught. But this is where you need to pay attention to the variables given in a problem. They are actively telling us to make that initial speed letter v. So we have to oblige with that, okay? But anyway, normally we would call it v naught. The car initially moves with speed v to the right when the driver observes a reason to make an emergency stop. At time equals 0, the driver fully applies the brakes. The car skids to a stop, traveling a distance d before fully stopping. Draw the forces acting on the car while it's in the process of skidding. Well, we have essentially two forces. We have a weight and a normal force, just like we drew before. Weight equals mg. Normal force balancing. Make sure your normal force balances the weight. Like this. And make sure that when you draw friction, make sure you draw it shorter than the normal force going to the left, because we were told that the car is moving to the right. I think we were told that. Yeah, we're moving to the right. So we're moving to the right, but we're decelerating or accelerating to the left. Okay, so the motion is this way, but the acceleration is this way. Okay, in part B, how will the distance change if, meaning increase or decrease, if each of the following cases? Explain your reasoning qualitatively, in other words, just using words. So what would happen to distance d if the car was moving twice as fast? Well, if the car is moving twice as fast, the distance would be greater. Now, the distance would be greater because it needs more time to stop. Part B2. What if the road is wet so that mu is less? Well, if mu is less, then friction overall is less. And if friction is less, this is going to make the distance greater. Now, this makes the distance greater because there is less force to stop the car. Part C. When the car skids to a stop, it has an acceleration of magnitude A. Now, we know it's negative acceleration because you're moving forward but slowing down as you do to come to a stop. But the magnitude of that acceleration is A. Write the equations for the following. C1. Write an equation of motion that relates V, A, and D. Well, the hint right here that we need to do to come up with this equation is that you have velocity, acceleration, and distance. Ladies and gentlemen, those are kinematic variables. And if those are kinematics variables, that's a constant acceleration equation that we're looking for. Now, what equation relates velocity, acceleration, and distance? Well, the way we used to write it, let me zoom in here, is we used to write it as v squared equals v naught squared plus 2 times a times the quantity x minus x naught. But we're going to have to change this into the variables that they want us to use. So first of all, x naught is 0. Second of all, x becomes d. A is still a, 2 is 2. V naught squared becomes v squared. And since we can't have two v squareds to, create confusion, we're going to actively call v squared v final squared, okay? So this whole thing now becomes v final squared equals v squared plus 2ad. Okay, that's what we have. Okay, so now since we know that the car is negatively accelerating, we can put the negative in for A, or we can just change the sign right here to account for that. So V final squared equals V squared minus 2AD would be one way to account for it, right? And we get that because 2 times negative A times D. Remember, A is negative because you're slowing down going forward. So you can account for that in the variable itself or in the equation. I prefer to account for it in the equation just because I can kind of get it all done in one shot. This is equal to 0 because you come to a stop. Final velocity comes to a stop. So we have 0 is equal to V squared minus 2AD. And if you add 2AD over to this side here, then you get V squared equals 2AD. Okay, that's our equation for that basically relates V, A, and D. Now, part 2, C2, is telling us to write a force equation. So now we're thinking Newton's second law here. Newton's second law tells us causing force minus opposing force equals MA. Looking back at our diagram, well, that's your causing force, and you have no opposing force because there's nothing on the other side. So I'm going to get rid of that part. The causing force would be friction equals MA. Now, friction, if you remember, is equal to mu times normal force. So we can rewrite this as mu times normal force equals MA. But if you remember from the diagram, normal force balances weight, so normal force is also equal to mg. So this becomes mu mg equals ma, right? Are you following the substitution here? First we substitute friction for mu times normal force, then we substitute normal force for mg. Okay, now once we get this far, you can go ahead and cancel some masses, and we have an equation that says, oops, let me get the right color in here, that says mu times g, A equals mu times g. Part 3, combine these together to get a formula for D in terms of V, G, and U. So basically what we have to do is we have to plug in the value for A, which is this, right here in place of A. So let's do that. This becomes V squared is equal to 2 times mu G times D. And when you solve for D, you have to divide the 2 mu G, and D is equal to V squared over 2 mu G. So part D, how does your answer to part C3 mathematically support your answer for part B1? Well, B1 was saying moving twice as fast means the distance has to be greater because you need more time to stop. So let's look at the equation. Okay, I'm going to write the equation down one more time. So d is equal to v squared over 2 mu g. If the velocity is greater, it's in the numerator. Greater squared means the distance is way greater, okay? They're going to be related directly. V is in the numerator. This is how we can say it in words. V is in the numerator. Therefore, more V means more D, more distance. Okay, and on the next part, again, analyzing the exact same equation, v squared over 2 mu g. For part, if we looked back at part B2, when the road is wet, you have less friction, so you have less force to stop the car. Therefore, you're going to have a greater distance as well. So if the mu is less, the denominator is less. And when the denominator is less, the whole fraction is greater. And sure enough, it supports. If mu is less, the whole fraction which is d is relating to the whole fraction of v squared over 2 mu g, is greater.